In the last lesson, we looked at a graphical method of vector addition. The graphical method is really useful to develop an intuitive sense of what's going on when multiple vectors act on a body and sum together. So if we have a look at this example very quickly, this blue box here is being acted upon by three different vectors. Now these vectors could be forces. When we sum these vectors together in a graphical vector diagram, we can join the tail of the first vector to the tip of the last vector to get the resultant vector. But this graphical method here is only really useful to gain an intuitive sense of how vectors work. If we really want to find the magnitude of this resultant vector here and its direction, we need to split up all these vectors here into their individual x and y components. And that's what this lesson's all about. So if we take one of these vectors, or just create a new vector, this vector r here lies somewhere on the 2D axis. Reducing this vector into its projections along the x and y axes is very useful when dealing with kinematics in 2 dimensions. We can, in fact, work in 3 dimensions and reduce a particular vector into the projections along the x, y, and z directions. But if you remember back to a previous lesson, we looked at how to solve various kinematic problems in 1 dimensions. In 2D and 3D kinematics, we can apply the one-dimensional kinematic equations of motion to each of the vector projections along the x, y, and z axes. And we do this independently of one another to find out how a particle moves in 3-dimensional space over time. But we will get to this in upcoming lessons. For now, we're going to focus on vector components and unit vectors. So this vector r here can be represented by its x component and its y component, where the vector r is the sum of rx and ry. So imagine our vector r represents a velocity, and this velocity is acting on a cannonball that's been fired from a cannon at an angle of 30 degrees from the horizon. So it leaves the barrel of the cannon at 200 meters per second. In order to determine the ball's flight path, we would split this velocity vector into its separate x and y components using trigonometry and apply the one-dimensional kinematic equations of motion separately to the x velocity vector and the y velocity vector in order to be able to plot its motion in 2 dimensions. So, for example, determine the maximum height that it reaches and also the range along the x-axis. So if we consider another vector now, and we call this vector A, we can use trigonometry to find the magnitudes of AX and AY simply because this is a right-angled triangle with an angle to the x-axis. So the magnitude of AX is equal to the magnitude of A, so the length of the A vector, cosine theta. And the magnitude of AY, the vector AY, is equal to A sine theta. And notice that the components here of A are scalar quantities. They represent the lengths of the AX and AY vectors. But we can also do the reverse. So for example, if we don't know the angle of vector A and its magnitude, we can use Pythagoras' theorem and the magnitudes of the AX and AY vectors here to find the magnitude of A. And we can also find the angle it makes with the x-axis using this expression here. And notice these values here are the magnitudes of AX and AY. Now, you might often see vector quantities expressed in terms of unit vectors. For example, vector A could be expressed as the magnitude of the component vector along the x-axis plus the magnitude along the y-axis plus the magnitude along the z-axis, where I hat, j hat and k hat are called unit vectors, which have a magnitude of 1. And unit vectors are used simply to indicate that a particular term, so one of these terms here, is a component vector of A that lies along a particular axis, whether that's the x-axis, y-axis or z-axis. They don't have any other significance or effect on the resultant vector. So as you saw at the beginning of this lesson, we used graphical methods for adding vectors together, and you could measure a rough estimate of the resultant vector with a protractor and a ruler. But we can also add multiple unit vectors together to get far more accurate results. For example, if we have these two vectors A and B, and we want to find their sum to get this resultant vector, we can break up vector A and vector B into its component vectors along the x and y axes, and add together each component to find the component vector of the resultant vector. So as you can see from this diagram, the component r vector along the x-axis is simply the sum ax and bx. And when we sum these magnitudes together, we can use Pythagoras' theorem to find the magnitude of r. Now, using this method, we can add many vectors together, so long as we break up each vector into its x and y components, and then add those x and y components together.